Okay, so this is a video on Lecture 7 looking at stress and strain, and it's really a top-level overview before you look in more detail at some of the aspects of stress and strain and things in your materials section of your course. And if you're following it, it's the Lecture 7 PowerPoint marked with stress and strain. But I mean, really, the first slide that we're looking at is looking at Hooke's law, and that'll be something you're familiar with from physics at school, where you've got F equals K delta X. And some textbooks call it an X, and some call it an L, and some call it an S, which makes it nice and confusing. But it's really just a spring constant K and a change in length of the spring. So the force applied by a spring is the spring constant and the change in length of the spring. And that's Hooke's law. So if I pull the spring twice as much, there's twice as much force to pull it back up until a point. If we jump on to slide 3 and you look at that graph, I'll try and reproduce that graph. What we can say for materials is that they have, for an extension, while you apply a force, there is a proportional region, a region of proportionality. That's your elastic region. And there is a proportional bit, and then there is a little bit more where it's starting to curve that's still elastic. So this bit here where the linear bit finishes is your proportional limit. So as I pull on my material, my spring say, in the proportional section, double the force, double the extension. I get to my proportional limit, there is still a little bit of elastic behaviour where if I stretch it, it will go back to its original shape, but it's not proportional anymore. If I increase the force, the extension doesn't increase linearly there. And then I get a second section here, and that limit there is my elastic limit. This is possibly the one you're more familiar with from GCSEs or A levels. But beyond that region, if I then extend it, it does all sorts of weird things. It doesn't behave predictably, and this bit is my plastic region. So if I continue to stretch, it no longer goes back to its original shape. Finally, we've got a final section here where it snaps, and that's our breaking point. And different materials have different shaped graphs. Some don't have a very big plastic region, some don't have any plastic region at all, they just break very quickly. That relates to the material properties, and that's something you'll look at more in your materials unit. What we're going to look at is some of the forces involved in that, because obviously they overlap with statics. So the first thing that you'll probably remember, or you may remember from your A-levels, is a factor called Young's modulus. You may have called it E, you may not. Which was stress over strain. And that was the same as force over area divided by the extension delta x over the original length. And we can rearrange that, and we can say that our extension of our material is going to equal 1 over the Young's modulus. Sorry, that shouldn't be an equals. F over A times X. That's meant to be an X, apologies for that. So we can start to think about things and work out how much a material is going to extend. And if you look at slide 5, it gives you some typical Young's moduluses, as well as shear and bulk modulus. I'm going to talk about what they mean. So Young's modulus is the one you're familiar with, which describes how a material stretches. If you have a go at the question on slide 6, that should be something you can already answer with the information you know. One thing that I have had to point out in previous years is that a wire is a circular cross-section. But then if you come back to this, I'll show you how to solve it. So you should have had a go at the tension in a piano wire question on slide 6 of the stress-strain lecture. With a 1.6 metre long steel piano wire with a diameter of 0.2 centimetres, and you're looking for the tension in the wire if it stretches 0.25 centimetres. So what would you do? We know from our previous slide, we know the Young's modulus of steel, E, and looking at that as 200 times 10 to the 9. We don't know our force, that's what we're looking for. So that's looking messy. We know our area is pi r squared, which is pi times 1 times 10 to the minus 2, 1 because it's the radius, squared. We know our original length, x, is going to be 1.6, delta x is going to be 0.25 times 10 to the minus 2. So we can use our equation from the previous slide. We can rearrange in terms of f. So if we rearrange in terms of f on here, in a different colour, we've got delta x e a over x equals f. So delta x e a over x. So delta x e a over x equals f. If I substitute my numbers in, we should get 980 newtons. Sorry, just checking that back in my calculator. I'm a couple of decimal places out on that. It's roughly 98,000 newtons or 98 kilonewtons. So that was the first question, example 12.7 in the lecture notes. You haven't missed some. I borrowed this from part of a larger lecture on materials. But if we go over a couple of slides, we can start to look at, we've got Young's modulus is stress over strain, which we've already talked about. We've then got the idea that we've used in structural analysis already, where something can be in tension, and if you cut it in half, then each half of the member is in tension. So we've already talked about that, and it's stretching throughout the object. So that's where you'd apply your Young's modulus when things are in tension. We've also got other forces which have other moduli associated with them. We've got compressive forces, so i.e. where it's in compression. And here your delta L is not an extension, but rather your delta L or delta X, whatever you wish to call it, is a change in length that way. That's the only difference between the equations. So rather than talking about, we draw like for like, rather than talking about an extension as your delta X, you're now talking about a compression as your delta X. The final one is, these on slide 10, the final one is your shear, which I'm going to draw two-dimensional because it will look slightly clearer. But it's basically as though you pushed over a rectangle or a cuboid. And, if I draw that in different colours, this is the original position of it. It's there. That would be where your original lines were. Obviously your force in this case is going to be pushing it sideways, it's going to be tipping it over. Your delta L in this case, delta X, will be the amount of tip in the direction of the force. Your original your original dimension will be the height of it. So that's slightly different in knowing where those numbers come from. So delta X is the amount that you're tipping it. X is the thickness of the material that you are shearing. A is the area that is in contact with the material. So it would be the top surface on this, because the shear, which I haven't drawn very well, the shear is being applied across the top here. So it's like rubbing your hands together. The shear is between the two surfaces. So A is the area of the surface under contact. If we then jump over another page, it talks about shear modulus and shear strain. Well, it's exactly the same principle, apart from they've given the modulus the letter G instead of the letter E. So for shear modulus, we say delta L, or delta X, is going to be 1 over G F over A L naught, where L naught or X naught is this length here, and delta L or delta X is this length here. And the final one that they look at is bulk modulus. Now obviously the difference in bulk modulus, which was also in the table, bulk modulus is to do with fluids. So if you imagine a fluid, it's no longer something that you might just squash on one side. This is meant to be a three-dimensional cube as opposed to a four-dimensional cube. But you're going to squash this, or you could squash this on all sides equally. So you've got to think about things slightly differently. In that respect, the equation is very similar, apart from rather than changes in length, it's changes in volume, an original volume. And you've got a negative sign in there, but you've also got delta P. And if you think about it, delta P is force over area, but it's a change in pressure. So this bit's your force over your area, which we had before, but it's a pressure now because we're applying it over a volume. So rather than working out a surface area, you're more likely to be given a pressure. Delta V instead of delta L because we're working in 3 dimensions, so there could be changes in the X and in the Y and in the Z direction, and V naught for the same reason because we're working in volumes. So that kind of covers the 3 different sorts of modulus. You've got shear modulus where you've got surfaces rubbing and they're distorting the shape of other surfaces. Tensional compression forces where you'll use a Young's modulus, or you've got the bulk modulus for fluids. Looking at slide 13, we then move on to fracture. So obviously if you're designing something, you want to pick a material that's not going to break. If you have a stress in that material that's bigger than it can tolerate, then it's just going to fracture, it's going to break. And it recommends here that when designing something, try to keep the anticipated stresses between 1/3 and 1/10 of the ultimate strength of the material. So if you jump to slide 14, there are some ultimate strengths. And you've got them in tension and compression and then in shear as well. So obviously what you want to be thinking about when you're picking the material you're going to use is how you're going to use it. Because if you see concrete, under compression is very, very good. Under shear or under tension, it's not so good. Still pretty good, but it's not so good. That's probably the one with one of the biggest differences. The other one to consider is wood. When you're compressing it, how are you compressing it? Whether it's parallel or perpendicular to the grain of the wood, because obviously that too will make a difference. So the next question, example 12.8, looking at breaking a piano wire. It's looking for a force. You've got tensile strength from previous slides, so you can work out the force needed to break the piano wire. I'll not talk you through that one because I think I will talk you through that one. Have a go and then I'll come back to the video and I'll talk you through it. So this is the information we have from the question 12.8 about breaking the piano wire. This tensile strength I took from the tensile strength of steel from the previous slide, from slide 14. There's actually some information in there that you don't need, but we've got the strength, which is a force over area. 500 times 10 to the 6 is going to be our force divided by our area, which is 1 times 10 to the minus 2 squared by pi. So our force is going to equal 157,079.6327 newtons. So what's that? That's 157 kilonewtons, which is bigger than the previous question, which had a smaller force on it, which means that earlier the piano wire didn't break. That's good news. Hopefully that made sense. We've always been talking about in structural analysis where we've had a member of a truss being completely in compression or completely in tension. What we haven't considered is the example in slide 16, where if you've got a beam like this and you're applying a force to it, it's going to bow like that. So this top bit is actually going to be shorter than its original length. So that's the original length. This bit will be slightly compressed in places. So this bit is under compression, whereas this bottom piece is being stretched, is under tension. So it's important to consider both the material and how you're using the material, what orientation it's in, the way the forces are being applied. And there's an example that that puts that into some context in Conceptual Examples 12.9. So it's talking about two walkways, one above the other in a hotel. So I've never been in a hotel quite this big, but attached to a high ceiling of a lobby. And it required a 14-metre rod. So if you imagine you've got a bridge here, and you've got rods, and you've got another bridge here, and you've got one big long rod that connects the two, here and here. So at the middle bit, on that pin, just here, you've got acting upwards to support a force of the middle platform. So this platform is only supported on this pin. Well, that's fair enough. I'll live with that. However, what they did is the rods, the long rods to the ceiling, were too long and difficult, and probably too expensive. Knowing builders today, unless you're a builder, in which case I apologise for that comment. They put two shorter rods and attach them with two pins. No problem there, I hear you say. Well, what you've got on this pin is also the weight of a platform. What you've got on the bottom pin of the right hand side is the weight of a platform, which is going to be pulling down on the top pin there. So on this pin, imagine that's your whole floor. So on this pin, this top pin, you're going to have the weight of the bottom platform plus the weight of the top platform, so it's needing to support twice the weight on one pin, which is obviously changing the way the forces are acting. So, and probably changing the tolerances and exceeding tolerances in places. So you've got to be aware of where the forces are acting, the magnitudes of the forces, how you're using them, and the materials you're using. Are they suitable for what you want to use them for? Example 12.10 talks you through designing in a little bit more detail using pine. You are going to need to look back in your tables from earlier in the lecture to find some of the numbers associated with pine. If you have a go at that and then come back to the video, I'll talk through how we go through it. So the first thing you'll notice we've done is find the shear strength of pine from the previous slide, the table. We then looked for applying that safety factor that it recommended. So if we apply that safety factor, then each support can exert a maximum force of 13,000 newtons. Okay. So applying safety factor. Per support. So that's also going to equal the maximum load that can be pulled down on. So the maximum will be 26,000 kilos, because 13,000 per support. Two supports, 26,000 kilos. Sorry, 2,600 kilos, because we've converted it to mass. Okay, dividing by 10. Obviously that's rounding slightly because we wouldn't normally divide by 10. Hopefully that makes sense. That concludes the first video on stress and strain. There is one more video on this lecture to do with Poisson's ratio, which I'll talk you through in a little bit more detail in that video. But that's the end of the first video on Lecture 7, Stress and Strain.